Okay, good, fine. Thanks for coming, thanks for the invitation, and thanks for the introduction. Yeah, as said, I will talk about how to make very large simulations using CP2K and the Submatrix method and all the developments we have conducted, mainly in collaboration with Christian Plessel and his co-workers at PC Square here in Paderborn. So, first of all, you may wonder why a theoretical chemist ended up giving high-performance computing talks. First of all, back in very old days of Phil Shockley, this wasn't uncommon. Yeah, for example, Gordon Moore, most of you know him, was also a chemist. Yeah, but for me it was quite different. I was always fascinated by supercomputers, and I wanted to do something with them, and was more in search of an application than the other way around. So, on a personal note, when I started doing computational astrophysics for my master thesis, I wanted to do something with having a higher hardware component within. And the first thing what was quite natural was lattice QCD, because back then there was then this QCD OC chip developed, which later on becomes the Blue Gene IBM computer. And then I wandered over this paper by Kenneth Wilson, and then it was written about ab initio quantum chemistry is an emerging computation area that is 50 years ahead of lattice gauge theory, a principal competitor for supercomputing time and a rich source of new ideas. And this really went into my head. And many physicists would object if it wouldn't be written by Kenneth Wilson, as a first of all Nobel Prize winner for renormalization group, but also the inventor of lattice QCD. And this was a statement directly coming from him. Yeah. You have to know that his father was a professor at Harvard in computational chemistry. But this was really one of the reasons I went into quantum chemistry. And it's really also why I'm going to talk about here, and this sets the stage. And the reason is that, in my opinion, in quantum chemistry is really one of the mother of all HPC problems, since it spans all levels of computation, from mathematical algorithms over physical concepts, to software engineering, which goes into these libraries and developing these codes, eventually up to hardware development. And in order to reach exascale, which is the target what we have here in Paderborn, you have to make substantial progress in all of these areas. It will not work if somebody comes with an exascale hardware and then tells scientists to put their best algorithms onto their specific hardware. And the other way around is even more rare, that very good algorithm, somebody does custom hardware just for a specific algorithm. This is simply because in this area, the wealth of algorithms and kernels is simply way too large. Yeah? In some areas like lattice QCD, that may be possible, but in quantum chemistry, that's not so easy. So this is really hardware-software co-design at its best. And this is the reason why these days my group is collaborating so heavily and well with the group of Christian Plessel and his guys at PC Square. So contrary to common belief, computer simulations are not a cheap or fast substitute for experiment, nor is the target to extend them into areas for which experiments are simply too complicated or impossible to conduct. Instead, my view, or the view of many of us, is more like of a computational microscope, where you can see the structure and dynamics atom by atom, and work together hand in hand with experimental colleagues to gain real understanding by rationalizing their experiments, and once in a while making a prediction, which is really the dream of a computational scientist, and hoping that this eventually will come verified experimentally. At the same time, this analogy shows really, in my opinion, the great appeal of computational sciences. Yeah, so we really can see that, because on top of the algorithmic improvements we're going to talk about today, you really can directly profit from the algorithmic increase from Moore's law in computational resources. So that really doubles up every 2 years. And if you think about a microscope, yeah, and for example, a real microscope, yeah, this is really like it would have about a doubling resolution every 2 years. So this is very hard to come by. And even though computer simulation are not a panacea, there's a lot of problems and shortcomings. The momentum is really great. Yeah, there's really great algorithmic developments, but there's also on top of that Moore's law, what we get on top of that. And this is really very rarely the case. And this is really the reason we are doing very big steps these days. I assume nearly all of you are aware of the fact that what we underlying have to do is to solve the Schrödinger equation. And this is a very innocent looking equation. And this is here, and we are making it even more easier. So we will in the following only talk about the time-independent version out of this Schrödinger equation. So the question is, what's the big deal? Yeah, and many of you may have heard about these statements made by Paul Dirac, one of the founding fathers of quantum mechanics. So that the fundamental laws necessary for the mathematical treatment of large part of physics. So everything can be seen as the equation for everything in terms of conventional matter, and the whole of chemistry are thus fully known, which immediately raises the questions what theoretical chemists are doing all day long for the money. The answer is also very nicely put forth already back then by Dirac, in the sense that the difficulty lies only in the fact that the application of these laws leads to equations that are too complex to be solved. And we have to do this when we want to do dynamics with that. We have to solve them many times. We want to solve them as quickly as possible. So the answer is, and this is how I make my money, is actually, and this is not so well known, is also said by Dirac. This was one sentence later, and this is not so communicated that often. Hence, it would be desirable to develop practical approximation schemes for the application of quantum dynamics. And this is really what we are doing. And I would say about as a community quite successfully so. If I would have the choice, if, for example, having the algorithms 20 years back and today's computers, or would have the computers 20 years ago with today's algorithm, I would choose the latter. And this is really like a manifestation of this statement already been made, that the algorithmic improvements are even more spectacular than the improvements we have in computing capabilities. And here they really unify and come together. And this is really the reason for the great momentum. So one of the best known approximations, and I don't want to go into details here, is the so-called Born-Oppenheimer approximation. If you know it, it's good. If it doesn't matter. So I just give you the idea. So basically the full Schrödinger equation can be dissected into an equation for treating the nuclei and one for treating the electrons. And you can, at your corresponding problem at hand, always decide if you want to treat the electrons classical or quantum mechanically, or the nuclei classical and quantum mechanically. And I think it's also here some sort of like the stage of the unification of the application we have in the in this atomistic compute center, which are basically in all of these areas. So mainly using classical nuclei. So this is conventional MD simulations. And on the other hand, this would be ab initio MD simulation. So that's what I'm doing. That's basically doing conventional MD simulations, but computing the forces using an electronic structure calculation. In physics, when people doing solid state calculations, they do the same. So they also approximately solve the electronic Schrödinger equation, but simply neglect the dynamics. Yeah, and so here we have the unification of solid state physics and of soft matter or biological chemistry or soft matter physics here inside. But this unfortunately goes hand in hand that the computational resources are even larger than the ones in the MD field, or the one doing solid state electronic structure calculations or static calculations. And as said before, my group is also deeply involved in the development of the CP2K package. And this really like is the software implementation of all of these areas. So this code is really like trying to separate out the electronic problem from the nuclear problem, and then you can arbitrarily mix them. So you have all sorts of electronic structure problems, from conventional MD simulations to very, very involved post-hard before quantum chemistry calculation, all of the calculation you know from the solid state physics community, and then can arbitrarily mixed with all sorts of sampling techniques, Monte Carlo, molecular dynamics, and very involved accelerated techniques and non-adiabatic techniques and so on. And on top of that, you can obviously also do all sorts of static calculations. This would be simply neglecting the dynamics of the nuclei, and then you would have what you are known from any electronic structure code for the solid state. Yeah, and here you can do this, and all of these techniques, and this goes on top of quantum chemistry, are typically designed for extended systems, so for the condensed phase, not for in the gas phase only. You can also, in most of the cases, have periodic boundary conditions, and you also have gradients available. So it's not a simple Swiss Army knife, as we've really seen before. It's really a very, very rich multi-purpose tool. Yeah, but today we are mainly talking about recent development and mainly talking about the technical aspects involved here. So what recently have happened is that there is now a full-fledged plane wave-based DFT code inside, which to my knowledge is the fastest plane wave code existing, and this is from design up, from ground up, heavily hardware accelerated. There's also now more and more development in very sophisticated post-Hartree-Fock or quantum chemistry technique, as said, with period boundary conditions and including nuclear gradients for going to very large systems. So the bold stuff is what I'm going to talk about in the following, are linear scaling algorithms to go for very large systems. There is no Carl-Parinello algorithm in the CP2K code. There's only something what is nowadays known as the second generation CP approach, which I have developed many years ago. There's now some recent development in Approximate Computing together with Christian. There's massive parallelism of very high degree of sophistication. There's sparse matrix algebra inside. There are specific libraries developed by the CP2K community, which in itself become very powerful. This is an open source project. You can download it for free at that website, and it has currently about 1.5 million lines of code, active code. Yeah, so that means the whole main algorithmic course consists of about twice as much. But we're constantly trying to keep the code as slim as possible. And at the moment, it's about 1.5 million lines of code. Yeah. There's also ever increasing investment in companion codes, for example, like the sparse matrix algebra, which have now spin off. Many of these libraries, which were developed by the CP2K community for CP2K in the beginning, are themselves projects which are quite substantial in size now. For example, the sparse matrix algebra library, which is only dealing with matrix multiplies, is now more than 100,000 lines of code. Yeah, and whenever you're making a commit, there's also regression testing been done so that there's no new memory leaks and something what had been worked on. So there's now a joint server infrastructure by the CP2K Foundation, joined by Paderborn, Zurich, and also the Paul Scherrer Institute. And there's about consisting of more than 6,500 regression tests. So whenever somebody's doing something on a source code, there's a whole cluster which runs through all these codes and looking that something what used to work is not broken and that there's no memory leaks included. Okay, so what the main driving horse here is are electronic structure calculations. So this is really, let's go here. Again, that's meaning treating the electrons quantum mechanically, so approximately solving the electronic Schrödinger equation. And you can do this statically, so this neglecting this equation, or you can do it dynamically. That's what we want. That means assuming statical classical nuclei. And so what you have to do, or the most common electronic structure techniques, which are mainly used in that specific field, are so-called effective single particle theories. And they go under names which you may or may not have heard, like Hartree-Fock, density function theory, and tight binding. So the main idea is, very abstractly speaking, instead of solving the many electron Schrödinger equation, you solve the much simpler single electron Schrödinger equation, electron per electron, and the interaction between them is then approximated depending on the particular theory. Yeah. Moreover, instead of talking about these very complex wave functions, so if you want to teach a computer to do these computations, and that's absolutely essential, they cannot be done otherwise, we have typically to agree upon a so-called basis set. So we describe this wave function as a linear combination of a basis set, so of basis function. If you and me have now agreed upon a common basis set, we don't have to talk about, in order to represent the wave function, only on the coefficients of this linear combination. And then the Schrödinger equation becomes a matrix problem. In fact, it becomes, since the Hamilton operator itself depends on the solution of solving this equation, a nonlinear generalized eigenvalue problem. So this is written here in matrix notation. So when you have agreed upon a basis set, only the coefficients are necessary, and then you have a very large matrix eigenvalue problem. And the simplest approach, or the direct approach, is to diagonalize it. That makes you make this matrix diagonal. On the diagonal elements, you have the eigenvalues. All other things are zero. That's why it's called diagonalization. And here, this is the coefficients of the so-called corresponding eigenfunctions. They are then arranged in the so-called orbital coefficient matrix C. And that's an n-cubic step. Why? First of all, because we have these eigenvectors in this matrix, they have to orthonormalize with all n-1 others. So then we have about n square pairs. And then the length of the vector and the computation which goes into one of these also normalization is also order n. And this is why we have eventually ended up order n cube. So the total energy from which all properties depend upon is then the sum of these eigenvalues. But since these guys are interacting with each other, corrected by a so-called double counting term, which depends on a particular effective single particle theory. So you can also write this now in matrix notation, and you can write this when these eigenvalues as a trace of a matrix product. And this is an n cubes step. So the idea had now been, instead of computing the eigenvalues and eigenvectors, and then later on form the density, if it's not possible to write the density rho, which in matrix notation is written as the density matrix P, to directly compute this matrix, which minimizes this energy subject to so-called idempotency condition. And the reason is, why is this better? And the reason is that the C matrices are rather full. The P matrices, even so higher in dimension, are rather sparse. In fact, this depends on the particular method of choice. They are not so sparse, but you can strictly prove that the interaction between electrons is long range but finite, so that eventually, if the system is just large enough, these matrices become sparse. And the whole field of linear scaling algorithm is exploiting the sparsity and then to reduce the scaling from n cubed to n to order n scaling. And together with my PhD students, Dorothee Richters, we had been working on very sophisticated techniques to make this happen. Unfortunately, these techniques are very, very sophisticated and complicated, not so easily to be accelerated by hardware. And this is exactly where the hardware-software co-design problem comes into. So here is a flow chart. So what we are talking about in the abstract. Yeah. So first of all, as I've shown before, this Hamilton matrix itself is not known. It depends on the solution of the equation. So how do you deal with that? So you guess an initial density, you build up the Hamilton matrix. That's a linear scaling step in itself when done properly. But the prefactor is medium in size. So for small systems, that's a dominating step. Then to diagonalize the system, using Scala-Pack, for instance, it's an n cube scaling step. You get all the eigenvectors out, and then you can compute the new density by simply forming the absolute value square, which gives you the density. And then you update the Hamilton operator, and then you iterate through that till you have reached self-consistency. So this is what is here. This is the so-called self-consistency iteration. And all of these matrices are dense, and then you're making use of dense linear algebra. The alternative path, what we are suggesting and had been obviously suggested for many decades and trying to exploit for many, many years, which unfortunately is not easy. That's the reason we are still talking about these things. Nobody has the solution for everything here, is to calculate the density matrix directly. And in matrix notation, this is a sparse matrix, and then you can devise a very sophisticated sparse linear algebra, and this opens the room for, in principle, make this linear scaling. And this is really a big deal, because you see, this classical effort, you can show you cannot do it better than linear scaling, and you now have, in principle, a formally exact quantum mechanical theory at a cost with obviously a much larger prefactor with basically optimal cost. Using classical MD simulation is in the same ballpark. Yeah, it's much cheaper, 10,000 times, or depends on the system, many thousand times. But my argument is this is what computers should take care of. Our problem is really to get to the linear scaling, and then we are in the same ballpark. So, and here what you see is really like coming together with PC square. So rather than using very sophisticated algorithms, what we have ourselves, you also have to say about us what can be eventually realized and hardware accelerated. And now you're doing the opposite. So you're taking a very simple equation, and this is now one way to compute the density matrix directly. And this we and others believe that this is the most practical way to get the best, to transform the problem the easiest into a computer science problem, and then really try to work together with these guys to get the best performance. And so what you see here is the only thing what you have to do is you have to compute inverses of certain matrices, which are very sparse, but or rather sparse, but substantially large. Then you have to compute also the sign function. So what's the sign function? The sign function is the matrix analogon of x divided by the absolute value of x, which you can also write x divided by the square root of the square. And in matrix notation, that's exactly what you have here. And so what you then compute is an iterative Newton-like equation, where you then can iteratively compute the sign function by converging exactly this one. And you see there's only matrix multiplications necessary. And then you directly get to the solution. And that's the idea here, is that you have now transformed this quantum mechanical problem into a matrix problem, and eventually the only operation what you need to do is eventually matrix multiplies very efficiently on rather big matrices, which are spanning from very sparse to nearly full. Yeah, and this really opens the door to having linear scaling as we want. We only have to deal with matrix multiplications. The drawback is that if you these computations are still very expensive and have to be done on massive paracomputers, and there you have internode communication, which are the limiting factor. And so the question is how you can make progress here. This, if you do it right, is how it looks like. So this would be here, for example, using scalar Prag routines. These are here with the numbers of atoms, the computational effort, and you see this is cubic scaling. That's pretty sizable on that scale. This about these linear scaling algorithms, and I think this already tells you if you want to go to large systems, it's unavoidable that you have to deal with these linear scaling techniques. Irrespective of what the prefactor of these techniques is, eventually the cubic scaling hits you. And this is what you see here. So you can do a pretty sizable system. That's depend now on the specific effective single particle theory you have at hand. So this is tight binding. Here to build up the Hamilton operator is rather cheap. And the matrices are more or less sparse. So here they are particularly sparse and low in dimension. DFT, which is the most popular electronic structure theory, is again effective single particle theory. These matrices are less sparse, substantially larger in size, and also more expensive to build up. But you can also go to pretty big systems, given obviously sufficiently big computers. Yeah, but that's what is necessary in the field anyhow. So underlying to make this happen is something what is called the DBCSR library, and I will quickly go into that. Yeah, so this had been developed because to basically optimize matrix multiplication as much as we can, and DBCSR stands for distributed block compressed sparse row. First of all, this is a strategy I will explain immediately. First of all, on the highest level, you have an MPI parallelization using certain techniques, which goes under the name Cannon algorithm, 2.5D algorithm, Karma, and very recently Cosma, which is the newest kid on the block. Here, the intent is to minimize the communication. And then on the node level, you have parallelization as much as possible, OpenMP. And this block compressed sparse row data format is such that you have block sparse where the blocks corresponds to atoms. And this is really now customized. This is not a solution for absolutely everything, but in the end of the day, we know we have eventually atoms at hand or molecules, for instance. And then one of these blocks eventually would then correspond to a molecule. We really like to exploit the structure. You don't see it as a fully mathematical problem, but you see about this is really custom made for the corresponding application. This is really necessary to get the highest performance. At the lowest level, on the other hand, you have then matrix multiplication, but very small but dense ones. Yeah? And then we have also developed libraries for multi-core CPUs and GPUs to outsmart or outperform vendor-specific BLAS libraries. And they go under the name like SMM, yeah, for CUDA and so on. We're going to talk about this in a second. So this is how it looks like really to achieve maximum performance. So for what you want to say about this, the intent here is really to compete with scalar Prag for dense matrices and completely set the standard for sparse matrices, because this is really the range of matrices we have to deal with. So for the distributed multiplication of two sparse matrices, there were several techniques been used. First of all, here, what I just said about is we're trying to reduce communication costs among these MPU ranks. And secondary, we would try to maximize performance of the communicated data on the node. The CPU part here on the node determines what needs to be multiplied and creates batches of works. And these batches are then handled by hardware-specific drivers such as CPUs, GPUs, or CPU plus GPU working hand in hand. To be more specific, this works here. We have this a cache oblivious matrix traversal to fix the order in which matrix blocks needs to be computed to improve cache locality. The corresponding multiplication are then organized in batches up to 30,000 small matrix multiplies. And this goes then to a scheduler, which makes a static assignment of these batches with the given A matrix roadblock to MPI threads to avoid data race conditions. And as said before, so the library had been now spin out because this now really also been usable for not just for sparse matrices, but even for higher tensors, which have some interest in the AI and ML community, and also because the development here is quite substantial. As said before, also the DBCSR library in itself is more than 100,000 lines of code in the meantime. Good. So at the highest level, how you do that. So this is, for example, how such a Hamilton matrix looks like. And in the old days, what people had been doing, they were using algorithms like McCuthill keys. So they were, for example, trying to figure out what is the permutation to make this matrix as diagonal dominant as possible. So trying to get all of these non-zero elements at the corners, mainly to the diagonal, and then distribute this over all the processors. Yeah. And obviously you can go to a couple of thousand cores with that, but this is not scaling to millions of cores simply because there's too few blocks available. So here it is really like the paradigm shift. You make something completely opposite. You make random permutation of rows and column block indices to balance the load. Yeah. So what you see here is you basically distribute this over the whole matrix. And then you have this 2D grid decomposition, and this is then distributed over all the P processors. And then eventually, then you have block sparse, blocks, which are then corresponds to physical or chemical entities, which are then atoms or molecules, which you can then further exploit. Right, and this is shown here. So this is, for example, how such a blocks looks like, and this is, and here, the non-zero blocks are small, dense blocks, and this then goes into these SMM libraries, and they are typically then of sizes 5x5, 13 times 13, and so on. So I would say about a somewhat larger small matrix block is something on the area of about 30 times 30. Right, and so you take really full advantage of the block structure sparse nature of the initial matrices. Yeah, so because we know that Hamilton matrices initially looks like that, and this is really like per design included. As said, we have all sorts of different matrices. So whenever we have this sparse matrix algebra, it should also perform when the matrices are dense. That's the point. And then you try really to make as best possible when you have very large systems and these matrices becomes eventually sparse. And you would like to scale up to a huge amount of numbers of processors to really make use of these supercomputers we have available at the moment. And for example, you see, for example, how this physical intuition comes into play. So when this is the initial sparse matrix blocks, you see that certain elements which are too far apart, that the interaction is rather small. The entries are typically rather small. So we set then this block to 1, and then you can control, that's an approximation, but you can control the approximation by threshold value as you want. You can make it arbitrarily accurate, or you can obviously make it somewhat faster to increase the sparsity. And then there's symmetry. All of these matrices are typically symmetric, so then there are certain elements which you don't need to compute twice, and so further gain efficiency. And then these things at the lowest level, then these smaller matrices are pretty small. And then, as said, we have then also inside the HPC community developed optimized libraries to outperform vendor-specific BLAST libraries for small matrices. And they go on the name like XSMM for Intel-based CPU and Knights landing systems. And this is now an Intel library because the developers now are in research engineer with Intel. There's also something like libQSMM for NVIDIA GPUs using CUDA. So this guy eventually ended up with Google. And now there is also libSMM ACC, which is an extension of the libQSMM for NVIDIA and AMD GPUs. And the main thing was that the AMD part was included for HIP. And there was all sorts of newer developments done. So this is now a follow-up version of the libQSMM. And this idea is really like that the LUMI system, CP2K is one of the very important applications there. And just to make this LUMI ready, then there's now in all areas been mainly worked by CSCS in Switzerland at the Supercomputing Center there, trying to get AMD support here. So the libx SMN generates executable code just in time. So we're doing at the moment quite a lot of these things just in time by assembling instruction in memory. AVX extensions are obviously supported. And what we achieve using just the CPU version is about a factor of 3 with respect to the MKL DGEM implementation on Knight's Landing. Approximately means on average over all of these different block sizes, what we are experiencing inside a realistic simulation. In all of these CUDA libraries, the main idea is some sort of like trying to overlap communication and computation. Yeah, this is for GPUs particularly important. There's all sorts of tricks which I can have no time to go into details here. The libsm ACC is obviously building up of all the ideas already put in the libq SMM, but there's also now just-in-time compiled code at runtime to fundamentally reduce the compilation time, but also to fundamentally reduce the library sizes. All of these GPU accelerated libraries, they have an auto-tuning framework to find the best parameters for every kernel. So M and K, these are the dimensions of these matrices. Some of them are squared, some of them are rectangular, and there are about hundreds of thousands of combinations out of that. And there are some, and the performance crucially depends on exactly these parameters. So these are about 7 parameters, which determines the optimal values for any specific kernel. And then there's various ways how they can be figured out what is a good kernel for doing the lowest level small matrix multiplies. Right, this is about how it looks like. So these are here for various different sizes. So these are exactly these M and K values for various GPUs. And so what you can see here, there's a couple of teraflops here. They are not that far off the theoretical peak. So it's doing a quite respectable work. And I think most impressive is what you see here. So this is really like this, the speed, but only on these matrix multiplies when you substitute the libx SMM on a Cray XT50 node, which has a 12-core Intel Haswell CPU and about NVIDIA V100, so it's a little bit outdated now. And as said before, the libx SMM is already an approximate factor of 3 faster than the MKL DGEM. So you're getting an additional factor of 5 speed up when you substitute this by the libsm ACC. Yeah, this is now, so to say, about a factor of 15. Okay, you cannot directly compare that, but it's that's really quite substantial, and it's obviously also much faster than cuBLAS. Right. So the question what we had been asked ourselves is, and this is because DBCSR can single precision, but it's mainly optimized for double precision. So the question we had here in Paderborn with Christian Plessel, if we can simply join forces and can do better than that, using our expertise he had and I had in approximate computing, and obviously he on the field of FPGA, which is a historically unique selling point of PC Square. So in Noctua, the current system, and also in Noctua 2, which has been delivered by the end of the year, this is the new compute center, it's nearly finished. Nearly looks like this one, have also big FPGA installation. Yeah, and Paderborn is always proud to claim that we have, at least in the beginning, the largest academic FPGA installation, which really offers the way to make approximate computing by defining certain custom data types. So rather than making matrix multiplies faster, and we were also investigating if we can do something on the DBCSR library in itself, but here the level has already been pretty high. The question is, can you do simply less matrix multiplies, and can you make them less accurate? Less matrix multiplies is if you can devise better iteration equations. Better iteration equations means better in the sense that they are faster converging. They need less iterations. And this is a master equation which we devised in my group many years ago, together with Dorothee Richters, so which allows to devise iteration equations for square roots, inverse square roots, for sign matrices, all of these things of arbitrary order, and all of these things comes out of that master equation. So you can then define Q roots. You can draw them simply by having of arbitrary order simply out of that master equation. And the idea here is that you can have faster converging equations which needs less iterations, but at the cost of having a little bit more matrix multiplies per iteration. And there's a little bit of a sweet spot. So you can do a little bit better than the direct equations I've shown you when going a little bit higher in order. The second one is what happens if you, for example, reduce the numbers of accuracy for storing a data and doing all the matrix operations, and with the intent of implementing them in an FPGA potentially. So the good news, first of all, is all of these things are leveling off. That means converging. So there's not something like that the inaccuracy in a certain iteration leads to blow up, which is not so clear as it may seem. So all of them are leveling off, and obviously you get more accurate the more bits you're using. So there's no news here. A sweet spot seems to be if you have doing matrix storage in a lower precision, but doing all the operations at full precision, so to say. That seemed to be particularly appealing because you nearly then get the same accuracy. But all of these things are leveling off. You have here really the area where you have quadratic or even faster convergence, and then you're getting to a specific level. And that means you can do much, much faster, less accurate calculation. And then the question is, can you live with that? And scientists in general, may it be physicists, chemists, or whatever, are always insisting on having the maximum accuracy. So if you tell them I have something with lower accuracy but faster, they're typically not impressed. The question is anyhow, can you still make genuine, credible simulations using these low accuracies? And this is where the approximate computing concept or paradigm comes into play. So in my field, I'm mainly interested in MD simulation. So I'm doing a huge numbers of these electronic structure calculations, computing energies and forces, and then propagating nuclei. And the question is really, and then I'm eventually averaging along these trajectories. I'm interested in ensemble averages, not in the accuracy of the individual calculation. And there's a very clever idea, I would say, which we were able to derive, which is actually an inverse of an idea I had many, many years ago, but completely employed in a different context. So what we have here in the first line is what is known as a Langevin equation. So we have an exact force, we have a damping term, and we have an additive white noise, which we add. And this additive white noise and the damping are not independent from each other, but they have to obey something what is known as the dissipation fluctuation theorem. So they are connected. So here, when you say about us, I have that specific noise value, then you are drawing additive white noise with a specific variance. And so the idea what we essentially had is when we're doing these calculations on an FPGA, but with lower precision, that the forces which we can get out can be thought of like the exact force, which we do not know. This would require the full calculation, plus a noise, which we do not know either. So what we say is about FPGA is the correct result plus an unknown noise. Yeah, but if we would know the noise, then we could simply then take the fluctuation dissipation theorem and then determine what is the corresponding damping we have to add in order to get a fully exact sampling of the Boltzmann distribution. So the ensemble averages, the properties we are computing, would be fully exact. Yeah, and the idea is to basically fix this damping term in such a way that the equipartition theorem holds, so that the mean value is about correct. And this is here shown. So here in red, we have the analytic Maxwell solution. And then in green, we have on a slightly different computation, we have the kinetic energy as it comes out of such a simulation. And you see the agreement is pretty good. And you really have to believe me, you have to carefully look into the distribution tails, and we really see that the agreement is pretty good. So that's this assumption that we can make less accurate calculation, low precision calculation. That can also been extended to GPUs, can also been extended to classical MD simulations, that such computations can be sort of like the exact forces plus a damping term, plus an additive white noise, and you have to figure out the correct damping term to get fully exact calculations. And this is shown here. So we have then added to the exact forces, we have then added more or less drastic additive white noise. And this is now such a very common property, the radial distribution function that measures at which distance we find the other atoms with the corresponding probability. And you really see, even though we take insanely high noise values, you essentially see that the observables are linearly not affected. So this deviation is nothing, it's within the statistical uncertainty you have anyhow inside the simulations. And that shows that this idea is very robust. You can make very, very high noise. As long as you're doing a credible calculation and you have very, very high noise level, you can essentially extract the complete exact observables. And that's also what you see in here in the autocorrelation. You have again exact forces. You would also see that the autocorrelation is nicely reproduced using these noisy forces. And you see again here the agreement is pretty good. Also what you see is the autocorrelation function decays to 0 rather quickly on the time scale of hundreds of femtoseconds. So there's not a very large memory, so to say. Right, and this opens now the door to make even more efficient calculations. And in the end of the day, without using dB/CSR. That's the reason I've not talked too much about these things, because our goal at the moment is to say about us, if we don't need the best matrix multiplication library, simply because we don't do the matrix multiplies, or we can do this very low accuracy, and there's some other idea I show immediately, then this is even better. And the idea here goes under the name Submatrix Method, which we have collaboratively developed over the last years. So this is here, for example, such a matrix, and I generally would like to compute a matrix function, taking that matrix as an input. The example, what we obviously need here of such a matrix function would be obviously here having the density matrix. So we're getting the Hamilton matrix in, and we're getting the density matrix out, and then we would basically have solved the problem. That would be such a matrix function. And the sign function is exactly doing that. So the idea of the submatrix method is now as follows. So we try to identify, so we basically say about it, we try to parallelize over all of these columns. So we cannot do this independently because there is interaction between them. So we try to identify, first of all, the non-zero values in every column. So this, for example, for processor number 1, for processor number 2, and this you see, you will figure out, if you haven't done so already, adds a very new degree of parallelism, which we can get on top of the parallelism we already have. So as said, these things are not completely independent, otherwise the problem would be easy. We try to figure out, when we, for example, say about this, the second processor have the second column, what information does he ideally need? So what is the minimum information he needs from all the other rows? Yeah? And so what we say is we try to compile what we call here the submatrices whenever the basis function have an overlap. So when these base functions are overlapping, then these guys are interacting with each other, and then obviously they have a non-zero block inside the submatrix, and all other ones are 0. And what you see here is that we can get submatrices out. This is the submatrix for the first column, this is the submatrix for the second column, and so on. So each of these columns getting their specific matrix size. You see they are somewhat different. This depends on the sparsity pattern, but if the system becomes larger, these matrices does not become larger, they're pretty constant in size. Then the idea is to independently apply the matrix function for each of these submatrices. And the trick is obviously these submatrices are obviously substantially smaller in size. Secondary, they can be independently computed. There's an additional level of parallelism, and they are very much compactified. So the elements of non-zero, they are very dense. So they become very dense, these matrices. And then you apply these matrix functions. So this would be then the, let's say, the density matrix for the submatrix. That's the density matrix for this corresponding submatrix, and so on. And each of these things can be done independently from each other. There's no communication at all necessary. That's why I say it's even better than dB/CSR. Not dealing how you can minimize the communication. Here's no communication between them. And then you copy the results back into the eventual density matrix. And you only have to do that, for example, only take these elements in the eventual matrix. So the process number 1 is obviously just communicating this vector, number 2 this vector, and so on. So there's also very few communication eventually necessary here, spawning this stuff out and then collecting it all back. And then you see obviously what is the approximation here. The sparsity pattern of the result matrix is the same as the initial matrix, which is obviously very good from a computing standpoint, that you know the sparsity pattern of the eventual matrix a priori, and it's having a very, very high sparsity, because the Hamilton matrix, when you're having a localized basis function, are pretty sparse. The density matrix, this depends on a system and can be pretty full. And then you are approximating it by a sparse matrix. And in the very beginning, we came up with the idea, we really had been facing a lot of criticism about that. And people were constantly saying about us, this can't be any good. Yeah, I mean, this is too much of an approximation. Only if the matrix is very, very well conditioned. So the problem is that your problem is not a problem, then this may work. If this becomes a hard problem, no chance to work, because this matrix becomes rather full. Yeah, and you making it by, you are approximating it by a sparse matrix. That it's fast, everybody believes. Yeah, but that it's good, that's not so clear. And the reason why we can show that this may work, or at least to motivate that, very quickly is if we can go back, let's say, to this slide. So what you have to compute is exactly this matrix. So what we say about this matrix is substantially less sparse than the H matrix, which is sparse from the outset when you're using the proper basis functions, is that we eventually need to compute the trace. And the trace of the matrix products, we only need those elements in the P matrix for which the much sparser H matrix is non-zero. So when H has a 0, I do not need to know the corresponding element in the density matrix because it does not contribute to the eventual observables. This is some sort of like very intuitive speaking why this is a good idea, yeah, and why, contrary to the belief of all others, this leads to astoundingly accurate results, yeah. And then the approximation, what is still inside, can be very nicely compensated by the approximate computing techniques I've just shown, yeah. But the approximation, and we have also, I think, in this 2018 paper, we have explicitly shown that the error on the observer you want to compute is astoundingly small. Right, so this is about the idea. I think I said all of these things. Yeah, suitable dense linear algebra. Okay, we can exploit dense linear algebra. We don't need to have any sparse matrix algebra anymore. Massively parallel, and obviously offers linear scaling, because if you're having larger matrices, you simply have more of the submatrices, but the submatrix in itself stays constant in size. And this really opens also the door to go to more accurate calculation. That means even if the computation here is very involved in itself, not linear scaling, cubic scaling, to the 4th, to the 6th, and so on, this stays constant. So it's a constant effort what you have to do. You have only linear scaling numbers of more of these submatrices. So even though when you're making very, very sophisticated calculation, this offers the way to have inherent linear scaling, even for techniques which are not linear scaling. There may be even the idea to have an exponential scaling technique here. You just have linearly more of these submatrices matrices where you have to apply them. So then Robert is, I think, this is the mastermind behind all that. So he has then also did something on the sign method, but I don't want to talk too much about these things, but he has mainly worked on GPU acceleration and how to make this the best possible. And this is really now what DBCSR from the version from 2020, where this was our first version, went to 21, when we try to keep this stuff as local as possible, do as much as computation on the GPU as possible and minimize the computation and so on. So rather than building up these matrices in the DBCSR format a priori and then distributing them over the different GPUs, we are basically not building up the DBCSR matrices, then do the computation on the GPU and then putting everything back in the DBCSR format again. We are building up the matrices already on the GPUs. So we're asking ourselves, what is the information necessary for GPU number 1, for instance, what he has to do all of this computation, and only these data is communicated. So it means only the vector on S and on the overlap matrix and the vector on the Hamilton matrix to build up these submatrices. Then you do the computation directly there. You extract only those vectors necessary, which they then to communicate to the host. And this again is a very, very tiny communication. So you try to do everything as local without resorting to DBCSR. Then you have here only dense matrix multiplies inside, and there's no communication necessary between these submatrices. And this is really what comes out. I think I'm a little bit late on time, so I think I will be done in 3 minutes. So this is about the maximum theoretical performance, peak performance you can get out. And this is about these peak performance what we get here for different matrix sizes. So these are the size of the submatrices. And you see these submatrices are much, much larger than the SMM matrices. That's why we cannot make use of SMM also. Here we are using cuBLAST plus a couple of tricks. Some of these submatrices are pretty large. And this is good because when you're having larger submatrices and very few communication, that's really how you can really get to peak performance. Yeah. So you see some of these matrices maybe not so maybe sizable. I mean, a couple of years ago, this was a genuine problem in itself, and now we call it a submatrix. But these GPUs become so fast, they are sniffing away these matrices, yeah, at a blinding speed. Yeah. So this is now on an A100. And so we were then thinking about is, okay, so now try to get large. So we were just trying to make a pre-exascale simulation. This is now the Joules system, have 936 GPU nodes, and we were asking them if we can get a sizable allocation. Unfortunately, they were only giving us 384 nodes, yeah, but it's still more than 1/3 of the machine, yeah. And we were looking about is what are the record holders in terms of peak performance. That's about 50 petaflops on Summit, 160 CPU cores, 22.8 GPUs necessary. I think these are chips, yeah. Any cores, and these are these are chips. And they're getting about 28% efficiency. There are some other which were better, about 50%, but on 5 petaflop level. And these were theories which are very easily to parallelize, again, with approximations. And so this is obviously what we see. We were scaling this stuff up to the 384 nodes we were given, and you really see that we have very good, strong scaling. So nearly perfect, strong scaling, wall time drops down, and we were the first in a quantum simulation to reach more than 100 million atoms. This is size even a classical MD simulation cannot easily do. I mean, there are not many MD simulations. These are also record resources necessary to do a classical MD simulation. This is now with an approximate quantum theory. And then what you see here is, this is about the peak performance, what you could have achieved, and what we get out is about 200 petaflops, and is about 43% of peak performance reached. And the question is why this is so. And the reason is because the average matrix size was about 600. So in order to get higher peak performance out, we have to move up the food chain to getting to larger matrices. And this is now where Tobias Kenter come into play together with Robert. So they were working on an idea to combine these submatrices. Many of them are rather similar and differ not by so much. And he's then combining these into individual matrices, which are a little bit larger. So then you have less matrices to compute, and you're getting larger in average size, and then you're getting more performance out of these GPUs. That's the idea. And then you have all sorts of a priori estimates when it's a good idea to merge these things and so on. That's an optimization problem in itself. And so on. So they have done that, and what you have seen about the average matrix dimensions went up from 660 to about 1200. So here, instead of the blue matrices, they are less, and they are becoming more here. These orange ones, these are those in the medium range. You have more of those, and in total you have less matrices to deal with in total. And when they came to me and then told me about they have about numbers of floating point operations reduced by 1.6, I wouldn't say about I was disappointed, but in the beginning, I have expected a little bit more given all the effort went into that. But then it struck me, 1.6 on 200 petaflop is more than 100 petaflops you gain in peak performance just by combining these matrices. And that's a genuine compute center in itself. So just having these ideas gives you 100 petaflops for free. And that's what we have here. So we have about here now 68% peak performance reached, 324 petaflops on a mixed precision FP16, FP32 on about 40% of the whole Joules machine. And this is really because now the average size is about here in the area about 1200 square matrices. And that's about it. So let me summarize. So using all of these techniques together, what I've just described, first, which we had been able to achieve 100 million atoms on using a quantum theory, having the highest sustained peak performance for 64 million. This was exactly this HIV virus in water solution. So everything is here. What you don't see, these are millions and millions and millions of water molecules, which are also explicitly dealt with quantum mechanically with about 68% of performance. This method of Robert I've mentioned to you. So basically trivial parallel, nearly no communication, do everything local on the GPU with dense matrix algebra. Very small approximation. The ones can be compensated with approximate computing. And we believe that we are now exascale ready. So if we would have a little bit more of those A100 nodes, then we can, let's say about 4 times as much, then we can achieve 1 exaflop in mixed precision, obviously. And with that, I would like to stop, and I hope to receive some questions. And sorry that I was a little bit too much in time.
Thanks a lot for this entertaining and enthusiastic talk. Are there any questions from the audience? Please, if you would raise your hand if you have a question. Jan.
Yeah, my question is, especially with molecular dynamics, sometimes customers tell us that their problem is just not bigger. So they have a certain problem size, molecules, things they are interested in. So my question would be, the performance comes by providing parallelism by larger problems. Is there a large fraction of the problems the scientists are interested in that need this scale? Because you need the scale to provide this performance.
Yep, I think
is it an artificial problem? So that you can reach this performance, but no one can because no one has a problem for it.
Yeah. Okay. Also this is, I think, is a very fair point. So what we've been shown, this record simulation is, for example, like yeah, this is the Formula 1, let's say, in this atomistic simulation. The average size is not so large, and having this periodic boundary condition, the vast majority of problems can be dealt with at much smaller scale. That's absolutely true. Yeah. So, and these peak performances you only get at these sizes. Nevertheless, even the average sizes are becoming up. There are, I would say, about a couple of ideas inside here, which and the time has to show that. Yeah, will be then coming part of the main distribution, but should become very valuable also for medium size. Secondary, speaking about these but you see, this technique is also very favorable that the crossover point is not so high. Yeah, so this was actually one of the problems was plagued by these linear scaling techniques in general, that the crossover point was unrealistically high. So what we have to a part of these ideas is also that the crossover point will also been reduced into an area which I believe is not is in the area of interest. The last part I would like to say is about for these post-Hartree Fock techniques I've not talked about. Many of these developments inside the DBCSR, also these ideas are generally very, very powerful. Yeah, so as I said, this does not have to be confined to the matrix function we had been evaluating here. And there's all sorts of post-Hartree Fock techniques which are heavily working on tensors using this DBCSR algebra. And here the computational effort, the size is not so large because the computation itself is much heavy, but the computation goes into a single calculation is very demanding, and they can make direct use out of these DBCSR techniques.
Okay, Robert?
I would just like to make a comment. So we actually don't need a particularly large system to get to this high fraction of the peak performance. Obviously, to saturate a lot of GPUs, you then in the end need a big system, but for the fraction of peak performance, we already get at rather small systems of about like a few 10,000s of atoms. And don't need millions of atoms to get to this high fraction of peak performance in the calculation. That's something to be aware of, that this technique would also works pretty well then for like intermediate size systems.
Also this is absolutely correct, but and this is a good point. Thanks, Robert. But obviously for many, this has also been a very large system. But development currently are ongoing also to go to DFT. Yeah, and here the matrices are less sparse, and I think that the point where these techniques becomes the way to go, in my opinion, is then much reduced.
Any more questions? I've got a question. Maybe I didn't get the point really about the reordering of matrix elements when you commented on people doing reverse Cattell-McKee, for example, to get the non-zeros closer to the diagonal right at the beginning.
Yeah, this was DBCSR still. Yep.
I don't see how you could distribute the matrix elements, do the renumbering in a more or less random way, get a very randomly distributed matrix structure, and then finally end up with blocks that still like have something to do with the original constituents, which are the atoms and molecules. So maybe I didn't get the point here.
Yeah. Also, this is exactly the complication what you have. So whenever, and this makes it also very hard, for example, everything you have to deal with. So you have to keep track on where your data basically is. Yeah? When you basically do these things, you have to basically have a Rosetta Stone where you know where these things are. So when you want to extract certain elements, then you have to really know where these elements are and getting them back by making the inverse way. And this is the reason why we nowadays really completely try to make these things based on dense matrix algebra without going back here on to the DBCSR library. Yeah, so that you don't have these format a priori and then redistribute that. Then you have to collect all of these data, all of these various cores, then do the computation locally, and then have then to redistribute them again. So we at the moment now building up all of these elements directly in local format, just asking what data is necessary on a single GPU. That's what we have here. Yeah.
Okay. More questions? All right, so we're also out of time, on time. Thanks again for your talk,
Okay.
and hoping to see you all again for the next talk in the Prof Lab seminar. Goodbye.
Alles klar. Ciao, ciao.